Okay, before I begin today, let me make a correction. Okay. So yesterday I gave the values of the units in terms of the fundamental units, and I had made a mistake in giving the expression for the Planck time. It's given by this over here, 5.39 times 10 to the minus 44 seconds. Okay, so let me now begin. So yesterday we had introduced the notion of co-moving objects. So co-moving objects are at rest in the t theta phi r coordinate. So co-moving objects. And let me remind you that in this coordinate system, the FRW metric takes a simple form. It's ds square as minus dt square plus a of t square times and we can also write this as minus dt square plus lambda of t square times 0 square over 1 minus k rho square over a naught square plus rho square omega square, where a naught is a of t naught. This is today. And lambda of t is a of t over a naught. So today we'll also introduce another notion, namely co-moving distance. So let's suppose that we have two space-time points at same time, so TA and TB, and we can take this point A to be, say, at R1 0 0 and the point B at R equal to 0, theta equal to 0, phi equal to 0. In this case, the distance between these 2 points at time t, which you can call d of t, will be given by a of t times integral 0 to r1 dr over square root of 1 minus kr square. Okay, just take the square root of this and integrate over r, because theta and phi are constant, so this doesn't change. So you can see that for fixed R1, that means if you take 2 points at fixed, which are co-moving points, so it's fixed at one point is fixed at the origin 0 0 0, the other point is fixed at R1 0 0. Then the physical distance between these 2 points changes as a function of time. In fact, it increases as a function of time. So two co-moving objects keep getting separated in physical distance. But we'll introduce the notion of co-moving distance. Say d naught, which is a dc, which is a of t naught times integral 0 to r1 dr over 1 minus kr square. So this is the distance measured in today's metric. And you can see that this remains fixed for two co-moving objects. The co-moving distance between the two objects remain fixed because we are measuring it at with respect to the metric at time t naught. Okay, so this notion will be useful later. Let me now give some definitions. So if we take this quantity lambda of t, okay, which is a of t over a naught, and if we consider the time which is not very far from t naught, okay, of course not very far means on the cosmological time scale, then you can make a Taylor series expansion. So the first term in the Taylor series expansion is 1 at t equal to t naught. Then we have some constant h naught times t minus t naught. Then a term proportional to t minus t naught square, and that will parameterize in a particular way, half q0 h0 square times t minus t naught square, and so on. Okay. So this is, of course, valid for t close to t naught. Okay, but close would mean in cosmological scale. So h naught has a name. So h naught is called the Hubble's constant, Hubble constant. And this measures the rate of expansion of the universe today. And its value is roughly 70 kilometer per second per megaparsec. Okay, so this is 10 to the 6 parsec, okay, which is 10 to the 6 times 3.26 light year. Which means that if you have two objects in the universe that's separated by this much distance, then on the average they move away from each other at a speed of 70 kilometers per second. The second constant, q naught, is called the deceleration parameter. So it's called deceleration because of this minus sign over here. And the reason that initially it was parameterized in this particular fashion is because it was thought earlier, that the expansion of the universe is slowing down. But today we know that q0 actually is negative. Which means that the expansion rate is increasing. Okay, so we say that we are undergoing an accelerated expansion. Okay, and later on we will see the reason for this. So now turn to some more definition. Okay, we introduce the notion of redshift parameter. Z, which is defined to be A of T0 over A of T. So this depends on the time period, okay, on time. So A of T naught over A of T minus 1, okay, which you can also write as 1 over lambda of T minus 1. Okay. So today, of course, Z is 0 because for T equal to T naught, you can clearly see that this is 0. Okay. And physically, okay, a distant object is said to be at redshift Z, to be at redshift Z if the spectrum of light we receive today from the object is redshifted by a factor of 1 plus Z. Okay, that means the wavelength is stretched by a factor of 1 plus Z. Okay, or frequency is scaled by a factor of 1 over 1 plus Z. Okay. So Z you can take to be as a measure of the time at which the radiation was emitted, or equivalently as a measure of the distance. Okay, the larger the redshift, the farther away the object is. Okay, because earlier the light would have started from that object. Now let's go back to the formula that we derived yesterday. Okay. So let's suppose that we receive light from an object at R100, okay, and we refers to 0, 0, 0. Okay, so we are at the origin. That's the way we have chosen our coordinate system. Okay, this can always be done because of the homogeneity of the metric. Then we saw that the time at which the light was emitted, okay, so time of emission is T1. If time of emission is T1, then we had derived the equation from the equation of null geodesic that T1 to T0 dt over lambda of T is A0 times integral 0 to R1 dr. Okay. So this one is a co-moving distance of that object. Now, if we have an expansion of lambda t, so let me remind you that we had postulated the expansion of lambda t of the form 1 plus h naught times t minus t naught minus half q0 h0 square t minus t naught square and so on. Okay. So using this expansion, okay, substituting this here, okay, we can see that we get a relation between, we can write the co-moving distance, okay, as a function of T1, okay, and that expansion, so it will be an expansion in powers of T0 minus T1, okay, because when T0 equal to T1, of course, the co-moving distance is 0. So it will be an expansion in powers of T0 minus T1, and the coefficient of expansion will be determined by these numbers. Similarly, okay, using this, okay, we can get an expansion for Z again in powers of t minus t naught, because Z is after all 1 over lambda of t minus 1. So you can just substitute and expand. And then you can eliminate the t1 minus t naught from this the two expansions and get a relation between the co-moving distance and the redshift. So let me write that. So by eliminating t1 minus t naught, we can get an expansion of the form so Z equal to A times dc. Of course, when dc is 0, then Z is 0. Okay? That means the object is on top of us, plus B times dc square, plus so on. Okay? So these coefficients are determined in terms of H naught, Q naught, etc. Conversely, if we know the relationship between the distance and redshift, okay, and this is in fact what we measure in experiment. If we know the relationship between distance and redshift, okay, then by looking at an expansion of this kind, we can calculate A, B, these coefficients. Okay, and then knowing the relationship between these coefficients and H naught, Q naught, etc., okay, we can determine H naught, Q naught, and so on. Okay. So this means that all these coefficients H naught, Q naught, etc., can be determined if we measure the relation between Z and DC. And this is what we measure experimentally, Z, the relationship between Z and DC. So now we'll turn to actual theoretical analysis of how A actually evolves with time. So we turn to time evolution of A of t. And what determines the time evolution of A of t is essentially Einstein's equation. So R mu nu minus half R G mu nu as 8 pi G T mu nu, where this is the energy momentum tensor. T mu nu is the energy momentum tensor. Now, I'll leave it as an exercise to check that for the FRW metric, we have R00 as minus 3 A double dot over A, Ri0 is 0, and Rij is A double dot over A plus 2 A dot square over A square plus 2K over A square times Gij. Okay, this is straightforward computation. You have to calculate the Christoffel symbol from the FRW metric, and from there you can calculate the Riemann tensor and the Ricci tensor. So this tells us that R, which is G00 R00 plus Gij Rij. Okay. So G00 of course is minus 1. Okay. And here Gij, Rij will involve a contraction of Gij, Gij. That's 3. Gij, Gij is 3 because Ij runs from 1 to 3. Okay. Using that, one can easily verify that this is given by 6 times A double dot over A plus A dot over A square plus K over A square. Now from this we can immediately see that if we take the I0 component, then Ri0 of course is 0, and Gi0 is also 0 because Gij, we wrote, let me write down the FRW metric here. So ds square was minus dt square plus A of t square times dr square over okay. So from this we can see that there is no Gi0 component. Okay. So this immediately implies that you must have Ti0 equal to 0. The other thing that follows from here is that if you take the Ij component, Rij is proportional to Gij. Okay. And here of course we have Gij. So Tij must be proportional to Gij. So Tij proportional to Gij. So let me now parameterize given this information. So we'll parameterize T mu nu as follows. So T00 we'll call rho. It's of course a function of T. Ti0 is 0. Okay. And Tij is another function which I'll call P of T times Gij. Okay. So now the idea is that we will substitute this in the expression in the Einstein's equation, okay, and see what we get. So we substitute into Einstein's equation. So I'll leave it as an exercise again. Okay, again, it's a simple exercise given the Ricci tensor components that I have already written down. The 0, 0 component gives you A0, A dot over A whole square plus K over A square equal to 8 pi G over 3 times rho. So this equation is what is known as the Friedmann equation. And then there is an Ij equation. I0 equation is trivial. So I0 equation gives you 0 equal to 0. And the Ij equation, both sides proportional to del Gij. So this gives you 2A double dot over A plus A dot over A square plus K over A square is minus 8 pi Gp. And now from here you see that because this is second derivative, this is first derivative, we can eliminate the second derivative, okay, by simply taking the derivative of this with respect to time. Okay, so that gives you generates a factor of A double dot. Okay, so that expresses A double dot in terms of A dot and possibly rho dot. Okay. So using that we can eliminate A double dot, substitute here, okay, and get an equation that involves only the first derivative of A. Okay, and possibly first derivative of rho. Okay. So use d dt of the Friedmann equation to eliminate A double dot from the second equation. Okay. and I'll give you the result. This is again a simple exercise. So exercise. So that this gives the following equation: d dt of rho a cube equal to minus 3 a square a dot times b. Okay. And later on, we'll see also the physical significance of this equation. Now, first, I'll say mathematically what this equation represents. So this again, I'll leave it as an exercise. Namely, to show that this equation follows from the conservation law of the energy momentum tensor, namely d mu t mu nu equal to 0. Okay. So this is again a straightforward exercise. T mu nu expression we have already written down. All components of T mu nu have been written down. Okay. This is covariant derivative, okay, raised with raised index. So you have to compute the Christoffel symbol and calculate d mu t mu nu using the definition of the covariant derivative. Okay. And you will find that the result that we get, okay, can be recast in this form. Okay. And this is not a surprising result because we know already that the Einstein's equation contains the conservation of energy momentum tensor, because if we look at this equation over here and take d mu on both sides, okay, we just apply d mu on both sides. Then the left hand side, this is identically 0 by Bianchi identity. Okay. And that means that the d mu t mu nu equal to 0, okay, is a consequence of Einstein's equation. Okay. So this implies that d mu t mu nu equal to 0 is a consequence of Einstein's equation. And this is what we are saying here. Okay, so this is the energy conservation and it's a consequence of Einstein's equation. Okay. So the two equations, let me remind you again, the two equations are a dot over a square plus k over a square is 8 pi g over 3 times rho. Okay, this is the Friedmann equation. And the other equation is d dt of rho a cube equal to minus 3 a square a dot p. This is the energy momentum conservation equation. Okay, in fact, this is really the energy conservation equation because this follows from the 0 component of this equation. When nu is equal to 0, that's the component that gives you this equation over here. Now we will try to understand the physical meaning of these various components of T. Okay, what they represent. So let us first try to understand the significance of Ti0 equal to 0. So Ti0 has the interpretation of energy flux okay, when you think of this as the ith component of the energy current. Okay. But because T is symmetric, okay, you can also interpret this as momentum density. And the vanishing of this, okay, is basically telling us that if you think of this T mu nu being produced by some kind of fluid, right, which contains, for example, all the matter that is there in the universe, all the radiation that is there in the universe, and so on, then the momentum density is 0, that means that in a given region, the number of the matter that flows from left to right, on the average, balances out the matter that flows from right to left. Okay, the momentum that flows from left to right by the various matter particles moving in is balanced on the average by the momentum that is flowing from right to left. Similarly, energy flux being 0, that means that the net energy flow from left to right balances out the net energy from right to left. And that's what we would expect in an isotropic universe, right? The fluid flows in all directions with equal probability. So there is no net flow in any particular direction. So this tells us that on the average, the source that produces T mu nu must be at rest in the co-moving coordinates. Of course, this statement is valid only in the co-moving coordinate, right? Because Ti0 equal to 0 is valid in this particular coordinate system in which you have written the FRW metric. You can certainly make a change of coordinate system in which this is not true. So Ti0 equal to 0 means that in the co-moving coordinate system, the net momentum density or net energy flux is 0. That means that the total amount of flow from left to right must balance out the amount of flow from right to left, okay, amount of energy flow from right to left. Okay. And hence, on the average, the source should be at rest. Okay. If there are objects moving from left to right, then there must also be objects moving from right to left on the average. So this is a consequence of isotropy. Now, Tij can be thought of as the flux of jth component of momentum along ith direction, or vice versa. And so given this, we now want to understand the meaning of what the Tij being proportional to Gij. So for this, it's most useful to go to a coordinate system. So if we take A of t to be slowly varying, then we can go to a coordinate system by reparametrizing r theta phi such that Gij is delta ij, okay? Basically local inertial coordinates, and in this coordinate system we'll get Tij as is proportional to delta ij, okay? Which basically means that Tij vanishes for I not equal to j. Okay? And so let's try to understand if this is what we expect. Okay? So recall that Tij is the flux of the ith component of momentum along the j direction. Okay? And what this is saying is that if this is our j direction, okay, and this is our I direction, Okay, I which I not equal to j. Okay. Then on the average, okay, the particles that flow from left to right, okay, carry no net pi. And the particle which flow from right to left also carry no net pi. Okay? And that's the reason why the flux of pi is 0. Okay? And this is of course what we expect if the momenta are uncorrelated. Okay, if for example if a particle is flowing from left to right, okay, that, of course it's not one particle, it's many objects that are flowing from left to right. Okay? They are equally likely to carry momentum in the upward direction or the downward direction. Okay, because whether it carries momentum in the upward or downward direction doesn't affect its motion from left to right or right to left. Okay? And that's the reason why the momentum flux of the flux of the ith component of momentum along the jth direction we expect to be 0. Okay? So this is again a consequence of isotropy. On the other hand, for TII, this is not true, because TII means this is the flux of pi along the ith direction. And now you see that if you have objects that are moving, for example, along the positive I direction, then they carry positive pi. Okay, so all the particles that are moving from, say, in the upward direction carry positive pi. And so the momentum flux is along the ith direction is positive, or pi flux is along the ith direction is positive. On the other hand, particles which are moving in the opposite direction, okay, downward direction, they carry negative pi, okay, but they also carry the flux in the opposite direction. Okay. So effectively, okay, the pi flux gets positive contribution from both objects or particles moving towards the ith direction Okay, when I say towards the ith direction, that means it has a component along the positive component along the ith direction, okay, or opposite the ith direction. Okay, so this is what this tells us. Okay, and that's the reason why TII is non-zero. Okay. So we say TII, we parameterize as TII as P. Okay, remember Tij was P times Gij, but Gij has been by coordinate transformation, we have made Gij equal to delta Ij. So Tii is equal to P, okay, times delta 1, 1, which is 1. Okay. And the fact that TII is I independent is again a consequence of isotropy. Okay. So isotropy implies that TII is independent of I. That's why it's proportional to delta Ij. Okay, so in a sense, the fact that Tij is proportional is P times delta Ij, or more generally Tij is P times Gij, is forced upon us by isotropy. Okay. So initially we had said the homogeneity and isotropy we had stated as a property of the metric. Okay. But because T mu nu is the source of the Einstein's equation, okay, once you have taken the metric to be homogeneous and isotropic, okay, the same property must be reflected also in the properties of the source, that is T mu nu, and that's what we are seeing here. So next, I'll try to give a physical interpretation of what this P means. And so to do that, let's imagine that we cut out, okay, let's imagine that the universe, the source of is a fluid. And let's suppose that we take a small box, small cube in that fluid and exclude everything from inside. Okay, so the inside there's vacuum. And outside is the fluid. Okay, that where you have the whatever the average fluid that describes the source in the universe, source of the TMU in the universe. So with this, let's try to calculate the force on a wall like this. Okay, so this, let's say, is the ith direction. Okay. And you want to calculate the force on a wall like this. Okay. So for this, let's imagine that the force on this wall will be due to the particles that fall on this wall. Okay. So it comes and hits the wall. Okay. And we'll assume that the wall is perfectly elastic. Okay, and because it's a box, it just reflects the particle back and it goes out like this. Okay. And of course, everything happens from the left because on the right, it's part of that box. Okay, inside the box, there's vacuum. Okay, so I am imagining that this wall is the left wall of this box. So everything is happening from the left. Okay. And let's suppose that this area is delta A. So, want to calculate the total amount of momentum, of the particles of the fluid hitting the wall per unit time. Now, by definition, TII is the flux of momentum, of the ith momentum along the ith direction. Okay. So you expect that the total momentum that of all the particles that fall on this wall should be given by TII times delta A. Okay, delta A, because flux means the momentum, flux per unit area, the momentum per unit area. So this is the total amount of momentum, okay, that of the particles that are falling on this. But actually, this is not quite true because TII gets contribution both from the particles coming from the right, from the left, as well as for particles coming from the right. Okay. But in this artificial system where you have excluded, where you have put a vacuum in between, inside the box, okay, you only have the particles coming from the left, okay, and nothing coming from the right. So you really get only half of this result. Okay, so this is the total momentum of the particles or of the fluid that is actually hitting the wall, okay, per unit time. So now we calculate the momentum transfer. Okay, so momentum transfer to the wall. Per unit time. Along the ith direction. So this will be given by twice this, because if it's elastic collision, okay, then the total amount of momentum that it carries back, okay, is exactly equal in magnitude to the amount of momentum that has fallen in the ith component of the momentum. The other components, of course, don't change, okay, but its sign gets reversed. Okay. So total amount of ith component of momentum gets reversed in sign. So total momentum transfer to the wall per unit time, okay, will be given by twice this amount. So 2 TII delta A times half. That's of course TII times delta A. Okay. And this means that the pressure of the fluid, okay, pressure is defined okay, in this situation, okay, as a force per unit area. Okay. So this is a momentum transfer per unit time. That's the same as the force that is exerted on this wall from the left, okay, along the ith component of the force that is exerted on this wall. Okay. So this gives the pressure, which is force per unit area, okay, is TII. Okay. So in other words, okay, P of T can be interpreted as pressure. So let me then summarize. Okay, so we had said that T00 is rho of T. Okay, now T00, of course, is the same as T upper 00. Okay. So this has a clear interpretation. This is the energy density. Okay. And we had said that Tij is P of T times Gij. Okay. And what we learned from the previous analysis is that P has the interpretation of the pressure of the fluid that acts as the source of T mu nu. Okay, later on we'll see what this fluid consists of. So with this understanding, we can, let me just show how we can understand the energy conservation equation in a simple way. Okay. So let's look at the energy conservation equation, d dt of rho a cube as minus 3 a square a dot times p. This I can also write as d dt of 4/3 pi rho a cube as I just multiply by 4/3 pi. So minus 4 pi a square a dot times p. So this you may recognize, okay, because rho is the energy density, okay, and 4/3 pi a cube, okay, is a volume of a sphere of radius a. Okay, so this you can imagine as being the volume of a fixed, I mean, it's the physical volume of a fixed co-moving volume. Okay, so take a fixed co-moving volume, so its actual volume, okay, will be given by 4/3 pi a cube. Okay, where a is time dependent. If you multiply by rho, okay, this is the total amount of energy that is inside a fixed co-moving volume. Okay. And what this equation is telling us is that the rate of change of that energy, okay, will be given by the right hand side, which is nothing but the work done, okay, because of the expansion of the universe, okay, and the pressure of the fluid, okay, there is a work that is being done by this fluid that is in the inside. Okay. And that's this. Okay, so this from this perspective, you can easily clearly see that this is really the energy conservation equation. It's telling us that the rate of change of total energy inside a co-moving volume is given by the work done by the fluid during the expansion. So this is energy conservation. So this is the informal way of seeing the formal statement that this equation basically represents d mu t mu nu equal to 0, okay, which is the same as the energy conservation equation. Okay, so now let me go back to the equations again. So we have the Friedmann equation, A dot over A whole square plus K over A square is 8 pi G by 3 times rho. Okay. And then you have the energy conservation equation, d dt of rho A cube is minus 3 P A square times A dot. So now if you look at these equations, you see that the number of variables that these equations have, number of variables is 3, because there is rho of t, p of t, and a of t. Okay, all of these are functions of time, so that's 3. On the other hand, number of equations is 2. Okay. So there is a mismatch. Okay, so that shows that just based on these two equations, you cannot really solve for these 3 variables. Okay, so we do need one more equation to be able to determine the time evolution. Okay, otherwise there are too many variables and too few equations. So we need a third equation. And this is where the interpretation of P as the pressure becomes important. Okay, because this third equation actually comes from what is called the equation of state. That relates P to rho. P to rho. So I'll give some examples, okay, and then we'll turn to the actual physical situation. Okay. So for example, that if the source of energy was radiation, then we know for the radiation that the pressure of radiation is rho over 3. And this is the relation we'll use. Okay, so this will be the third equation for that will supplement these 2 equations. Okay, and once you have to be equal to rho over 3, then you can solve these equations starting from a given initial condition. The second class of examples that will be important for us is if the source is non-relativistic matter. Non-relativistic matter. So non-relativistic means, so non-relativistic here basically means that the velocity is small compared to the speed of light. Okay, slowly moving objects. Okay, or in our notation, this of course has been set equal to 1, so velocity is small compared to 1. So let's see what kind of pressure energy density relation we expect in this case. Okay. So let's, just for the sake of argument, assume that as if this is an ideal gas. Okay, even though it is not too important. Okay, the result that we'll get will be valid even without making this ideal gas approximation. Okay. But if you have an ideal gas, okay, then the rho, because these are slowly moving, okay, energy density basically comes from a rest mass of objects. Okay, and let's imagine that it's a collection of protons, okay, or some other object. Okay, but typically it's a collection of protons and neutrons. Okay, electrons are very light. Anyway, so rho is given by roughly by m times n, okay, where m is the mass of the particle, mass of proton or neutron, and n is the average number density of proton and neutron. And in practice, for our universe, this is an exceedingly small number. It's, I think, about 6 per cubic meter. Okay, so its universe is really very dilute. Okay, even though locally, of course, it can have high density, like on the Earth or in the middle of the stars. Okay, but most of the universe is empty. Okay, and on the average, it has 6 per cubic meter of protons. Anyway, so this is the expression for rho. Okay. On the other hand, the pressure, okay, if it's say at temperature T, okay, it will be given by the ideal gas equation of state, so n times kb times T. So P over rho, you can see, is given by kBT over m. Okay. Now this object is average kinetic energy. And for non-relativistic matter, by definition, okay, average kinetic energy is much smaller than the rest mass energy. Okay, again it's mc square, but I can see has been set equal to 1, so it's much less than m. Okay. And so you see that P over rho for non-relativistic matter is much less than 1. Okay. So we say that non-relativistic matter has equation of state that is P equal to 0. Okay, because P of rho is very small. Okay. So this is the equation of motion we'll be using for non-relativistic matter. Okay. And a major component of the present universe, okay, is made of non-relativistic matter, okay, which are the stars and the planets and various other objects, but mostly it's the dust or the essentially hydrogen gas, okay, that fills the most of the space, okay, because most of the space is otherwise empty, and that's where most of the mass comes from. Now I'll introduce a third component, okay, which you know also is present in our universe. And this is the cosmological constant, which is also sometimes called the dark energy. Okay. So this, to begin with, arose as an equation, okay, as an extra term in the Einstein's equation. Okay. So if you take Einstein's equation, r mu nu minus half r g mu nu equal to 8 pi g t mu nu. Okay. Then without loss of generality, without breaking general coordinate invariance, you have a choice of adding a new term here, which can be written as minus 8 pi g lambda times g mu nu. Okay. This clearly doesn't break general coordinate invariance, okay, as you can see, because g mu nu is a tensor, is a rank 2 symmetric tensor, just like this side. Okay. Its covariant derivative is identically 0, okay, so it doesn't violate Bianchi identity. Okay. So this is just a constant, so lambda is just a constant, okay, which is called the cosmological constant, which is a new term to the Einstein's equation. Okay. But it's also useful to write this as a term of the form, I mean, in this form, T mu nu plus T lambda mu nu. But T lambda mu nu is a new source of energy momentum tensor that is given by minus lambda times G mu nu. Okay. So it's as if besides the usual matter and radiation that he had already introduced, okay, there is another component of the energy momentum tensor that's simply proportional to minus lambda times G mu nu. So this is what is called the cosmological constant or dark energy. So if you want to write it in the form that we had introduced earlier, okay, so T00, remember we had our notion of T00 is rho, okay, and so you see that now rho has got a new component, okay, which I'll call rho lambda. Sorry, T00 is rho lambda is minus lambda times G00, okay, but G00 of course is minus 1, so this is lambda, and Tij was P times Gij. Okay, again comparing this, we see that P has got a new component. Okay. So the pressure associated with cosmological constant is minus lambda. Okay. And this means that the equation of state that the cosmological constant satisfies is P lambda equal to minus rho lambda. Okay, because rho lambda is lambda, okay, and P lambda is minus lambda. So this is the equation of state for the cosmological constant. Okay. So to summarize, okay, we have introduced three separate kinds of source. Okay. For radiation, PR is rho r over 3. For matter, PM is 0. And for cosmological constant, P lambda is minus rho lambda. You see that this has negative pressure. This is the only component that we have introduced so far which has negative pressure. So this is where I'll stop today, and from tomorrow we'll take over using these equations. We'll substitute these into the Friedman equation and the energy conservation equation and see what we can get from there.